What do you think? Other guys gonna come or should we start? Okay, then we can wait maybe another 5 minutes. But meanwhile, if you have any question or anything, we can. Nothing? That's good. Modeling systems engineering and simulation. So, yeah, this is our objective. Today's lecture objective. I think I should. Okay, system and simulation. So I think in the first lecture I have showed you some kind of diagram like this, the system and the component. So normally, if we consider a system, this system is supposed to have some input and have some output. Then the system component actually functioning to give some kind of output. And of course, system is supposed to also consider the system boundary and environment, all these things. So the thing is here, during simulation, what's wrong? It's a little bit slow. I don't know. It's not working. Yeah, my computer is actually today behaving weird. So what's happening? Yeah, now it's working. Okay, consider, this alpha theta theta all are our system components. And during the simulation, we try to figure out how one component functioning with other to give us some kind of output, our desired output. So you see, without system, you cannot actually simulate something. So the fundamental thing for simulation, you have to understand your system. So without understanding, you cannot really simulate. So sometimes people think like we can simulate everything, but it's not possible. Of course, you have to design a specific system. And for designing a specific system, you need models. And the computer is supposed to understand those models. So this is actually the relation between system, models, and simulation. We'll try to figure out different types of simulation in part. Oh, come on. Really? I don't know. Okay, so now we try to see what the other people is telling. The definition of simulation, but is it the second one? Yeah, I think so. Yeah, I think so. This is the second one. So before going to the definition, try to understand. Let's say somebody is sick, and we know the symptom of fever and cold. So if we wanted to simulate the situation, so what do you think? If somebody is pretending that he is having fever and he's making all kinds of behavior, how a person, if somebody is affected with fever or cold, like coughing or he is pretending that he's got fever, like high temperature. Do you think this is qualified that he is simulating or he is simulating the fever and cold? Or do you think this is something different? If you do not get my question, feel free to ask. I will clarify because this understanding is very important to understand the simulation. Yep.
The first thought would be she's sick or she's ill.
She is not sick. She's pretending that she's showing that she has high fever. Like all the school time when you do not want to go to school, try to pretend that we have fever. Like I actually didn't like to go to school. So something like this, something that is talking. Do you think this is a simulation of fever and cold? Yeah. Hmm? Yeah, this is right. This is not because simulation means you have to create the similar kind of environment that your system will produce or how your system will function in this particular environment. So you see, pretending is not simulation. The simulation, according to our definition of model, we know that model is somehow representing the reality, right? Simulation is exactly doing the same thing. But here, we know how one component to other component is, influencing or how the behavioral things are progressing from one component to other component or subsystem level to component level. So it depends like where you are focusing. Slowly, we're gonna try to understand like which specific space we have to focus during simulation. So now let us read the simulation here. You see a simulation imitates the operation of real world process or systems. So these two things is like when you are talking about the process and systems, try to be interlinked because most of the time the processes and the systems are pretty much same. But when you are going to talk with I don't know, so industrial designer, normally they consider processes means the factory. So little bit careful with the processes and systems. Okay. The model represents the key behaviors and characteristics of the selected process of system, while the simulation represents how the model evolves under different conditions over time. Very nice definition. So another one, simulation is nothing but an experiment with the help of computer without performing an actual experiment. This is in a way right and way wrong because when we are dealing with the word prototyping, the prototyping also kind of experiment, and this experiment you can do with a scale prototype or with a physical model or with a computer model. So this is not always true, but yeah, most of the cases this is true. When we are talking about simulation, we think that we create some model into computer and see how it, what's the behavior. Then simulation, part one is simulation is the process of creating a model, an abstract representation or exact copy of an existing or proposed system, a project, a business, a mine, forest. So the definition of the system. In order to identify and understand those factors which control the system and or to predict the future behavior of the system. This is also very good definition. This includes what we are doing normally in a simulation. We create models, then we try to see the behavior, and the outcome is normally we try to predict and we try to make some this is here a small simulation. You see here like the world, here our solar system. So this is actually kind of simulation, but this is this does not have this do not have any output. So we cannot actually predict something out of this rather than a graphical presentation. But still, this this kind of thing also goes under simulation. But I think it would be right to call them animation. So animation and simulation seems like sometimes they are using um, they carry the same meaning, but in a specific cases it is not. So a little bit careful and use of simulation. So why we use simulation? We want to answer some questions. So when we start with a system, system is most of the time the solution of the problem. So simulation actually give us some kind of answer, like how your system gonna function or behave with a certain condition. Then we can make decision out of simulation. You see, when interdisciplinary team, let's say electrical engineer, software engineer, mechanical engineer, they're working together. So different team working with different things for a system. Let's say if you consider a aircraft system. So let's say the structural engineers who is actually I don't know involved with mechanical design. If they are telling that the wing supposed to carry the load of I don't know 500 kilograms of load or force, then do you think this is really feasible to talk like that? So normally he's supposed to come with some kind of hand calculation, but when he's doing the hand calculation, it is very time consuming. Rather doing hand calculation, if he or she could do some kind of simulation and show the whole structure to the team, then you see the software engineer also would understand the critical point of the design, and maybe the critical point they wanted to install some kind of sensor to detect the material change or material behavior change over time or due to stresses. So you see the software engineer still could have the idea like this. So simulation is also similar to the modeling. It's a graphical representation. So we try to see something. So with modeling, people also mathematical modeling people also say it becomes simulation, but it is hand calculation. It is not really simulation. Sometimes they use this word, but it is not absolutely correct. Okay, decision making and understanding. So I think without understanding, you cannot make the decision. Then experimentation and test. I think this is the most important thing why we are doing simulation. And if you have you anyone started with any modular systems engineering book, like only for interest, maybe? You will see most of the time. I also put some graph in past class, like how they try to figure out this modeling system actually reduce the product development cost over time, because you can make some early decisions. So simulation is the one of the main parts, or I would say for making decisions. Without having simulation, it's really very difficult. Like with enterprise architecture, to make some models and try to understand your system. I think it's going to be really very difficult. So experimentation and or taste is the main part of the simulation, because you try to drive some kind of solution, some kind of decision out of it. So therefore, we are using simulation for those things. Then predicting the effect of change, this is also necessary. So how one component or subsystem is actually affecting the other system, that you can also identify stakeholders buy-in. This is also very important. Normally in a big project, like when we wanted to build, let's say, again, I'm trying to saying like you need at least at least 500 million. So if you think of a aircraft to develop, so you see like scientists like us or any small company cannot dare to invest so much, 500,000 euro, sorry, 500, not 500 million euro for the product development. Right? So if you wanted to go up to the manufacturing part, then you have to do so many steps like product development. So if you have some quite good simulation, let's say if you have some good efficient engine of your aircraft or efficient wings, so you can show those to your potential investors and you can tell them, see, our product is really different than the current product in the market. So you can easily invest here. So people can actually trust you. You see, these people maybe do not understand this whole thing of simulation, what is going behind the simulation and how people are doing simulation. But the result is very important. It is not only for the engineering team, rather for the other stakeholders. And you have seen in our previous classes that systems engineering not only considers about the engineering problem, they try to bring in all the stakeholders into the whole system workforce. So here I think quite important work. It is wiser to perform simulation before going for an So that's why people do simulation, and you will see many companies are investing huge amounts of money for simulation because they try to understand their product before going to the implementation level. Okay, I think through this discussion, it is quite clear that when you need a simulation, but I also try to explain when a system is complex, then we normally need simulation. Let's say I don't know. Let's say yeah, you try to design this one. I don't know what does it call. That stand for the speaker, or I don't know what does it called, microphone. So this microphone stand you wanted to design, and for this I think if you have a good lab, you do not need to simulate. I think you can choose some materials and pipes and make some stress test and apply some kind of load, and you will get your expected result. But simulation is normally we are doing when the system is complex. So for simple system, simulation is not so necessary. Sometimes people are doing it, making their life difficult, but it is not advisable. So when knowledge gaining is necessary for further physical implementation. So this is also related with our last one. Then when designers have several options. So in design, we need to do PDR and CDR. I think you already heard about this thing. So preliminary design review. So when we have some kind of options, so we try to figure out which option is better for our solution. So then we try to do figure those options through simulations. Then when knowledge transfer is necessary, so visualization, that is also discussed in the last slide. Okay. When simulation is not an appropriate tool. So if you see this animation, so do you think like walking through this for making decision, do you think this, I don't know, the cat or lion supposed to calculate something that he's supposed not to go over this, I don't know, what does it call this, art erosion? Is it necessary? Is it very simple? So there we do not need any simulation. So where you can use your common sense, simulation is not really necessary there. So when the problem can be solved by common sense. So this is common sense. Sometimes, we have to use our common sense in engineering. This is quite common also. Then when problem can be solved analytically. So if you can make the calculation with your hand, if it is not complex enough, then you do not need any simulation. When it is easier to perform direct experiment with the physical system. So sometimes it is wiser to have the physical experiment rather than having simulation with computer, because to do simulation, you need to create right models, you need to create right environment, then you're supposed to run the simulation. And if you see that without doing simulation, you can run a test with the physical system and it is easier, then you do not need to do the simulation. But of course, here you have to think, like, if you run on one time the simulation, you can use this result for 1,000 times. But if you run a physical test with your physical system, then it is broken after one test. So you cannot use this one, or you cannot tweak different settings. So this is also you need to consider. When the resource time and cost exceeds saving, so normally we are doing simulation to somehow reduce the cost. But if it goes beyond saving, then simulation is not necessary. If the learning curve is high, it is like we are working for one simulation publication since almost 1.5 years. And end of the last week, and one single simulation actually took almost a month to run like CFD simulation, because our computer is not so high configuration. And after 1 year, we have seen 1.5 years, we have seen the last part is totally wrong. We have to again start, and it will take another maybe 3 to 4 months. So you see, the learning curve sometimes is really very high. Simulation is not so easy. Some simulation is easier, I would say, related to finite element analysis. But with CFD, it is really, I would say, very difficult. I will show you some examples, then maybe you understand. Again, in previous slide, we are talking about when system is complex, we are doing the simulation. But you see, when the system behavior is too complex, I think it's better not to do the simulation.
Yeah. Yeah. So you have to be really careful of what you're doing. What else can you think also?
I think it's a very good question, actually. So you're gonna figure it out also in later.
So the important thing is don't this clear today.
No, it's not CFD, it's FEM, FER. Right.
So it is also important if you have any question or something is not understandable, you stop and ask them.
Yeah. Yeah. Thanks.
Okay, sorry.
No worries. That's very good discussion. Okay. When the simulation result evaluation is not possible. So you are having some simulation result, but you cannot evaluate.
So normally, as you have done the simulation with CFD, you see you have to also what do you call evaluate your result. You have to prove that the result what you got is correct in relation to maybe other result, or maybe you can apply some kind of what do you call um, some kind of regulations. Maybe the regulations also have some limits, like this kind of a structure with this kind of material could have this kind of stress limit. So for finite element analysis, there are some certain rules you will find. So there it is possible. Okay, then challenges of simulation. So this is one CFD simulation what we have done, and this is the wind tunnel test. In the last slide, I was talking about the evaluation. So normally in CFD simulation, it is not mandatory, but if you wanted to develop a product, then it is mandatory to do some kind of computer simulation and try to simulate in a wind tunnel the same boundary condition, and compare with your computer simulation output to the wind tunnel test output. So this is kind of norm in the industry. So this is also not so easy. So model building, the first is when you wanted to do simulation, you need models, and model building is not really easy. The simulation results could be difficult to interpret. Sometimes, yeah, with CFD simulation, I am also do not understand what's going on, and it's really very complicated to me, honestly speaking. Sometimes the results are not really too easy to interpret. So you need really long time with enthusiasm to understand the result as well. And yeah, and most of the time people fail due to those passions. Then simulation results, verification and validation. So virtual to physical analysis is not straightforward. It's really very difficult. And I can also give you another example with like one simulation we try to do with the wind tunnel. It's the company name RAS or something like. It's in Vienna. And do you know how much they asked us for 1.5 day simulation? So they will take 6 hours for the model preparation, and we have to create the model. Only they will set up the model, and it will take half days. And another half days they're gonna run the simulation, and they are asking us 40,000 euros, 1.5 days. So you see, like it's really like 40,000 euros. It's not fun, really. So okay, what can be simulated? That's quite interesting. Any system or process that has a flow or event can be simulated. What I was talking in the first slide, that the behavior, if the system is static, you do not need any simulation, because you understand what's going on, because there is no movement. So normally we are trying to figure out the problem when there is movement. So the system components level or subsystem level, they have some kind of interaction between each other, and from those we can predict, their future behavior. So, however, simulation is most effective when applied to process or equipment that change over time and have variable factors and random inputs. So this is also almost similar to the other part, the first one. Then simulation can be used to manage processes, procedure, and assets. So it is quite often we are doing some kind of procedure if you wanted to see how things function, like after one phase to another. So in SysML, it's quite easy to do that, or enterprise architect or CAMU system modeler. But if you really wanted to simulate a process in SysML model, I would say it will be really very difficult. It won't be impossible, but I think it will take a long time with many people's effort, and you need different expertise, because you have to identify, let's say, if you wanted to do some kind of, I think, some of parametric modeling, we can do simulation, right?
Yeah.
So let's say the finite element analysis, maybe you can do with SolidWorks. So then you have to define your model, the model, what do you call the physical part, like the dimensions, and then you have to create some kind of formulas or apply some already defined formulas and try to find out the changes. Whereas if you use the CAD software, then you can do it quite straightforward. That I will show. So also the tool selection is quite important for different types of simulation. And areas of application, normally we are considering systems and systems environment. So we are doing simulation for mechanical parts, for aerodynamics, electrical circuit. So these three things, more or less, you can do with SolidWorks. But the aerodynamics or CFD simulation is not so good from my understanding, because we cannot do so many things with SolidWorks, or maybe I didn't figure it out. But I found ANSYS is far better simulation tool for CFD, for aerodynamics simulation. Electric circuit simulation you can do with SolidWorks. I do not know. I have seen some videos, but I never done. But I think electric circuit simulation, it is better to do in what do you call? There is another software, MATLAB Simulink. The Simulink is, I think, quite straightforward. So if you have a good understanding on the logic of electrical circuits, then you can design the circuit quite straightforward.
Also now probably the Modellica.
Yeah.
So you have a lot of different tools, like we already told you. And it is depending on what we want to get, which tool is most preferable.
Right.
Okay.
Then business processes. Normally there is also a language for business processes, or BPM or BPM or BPM. BPM, yeah. So this is something I think enterprise architect also covered it. Yeah. So then healthcare, education, transportation, modern traffic, this is quite, it's another area, but there are many simulation work out there. Then network simulation, especially for wireless network and PSTN, LAN, people normally do the simulation also.
Okay, then simulation classification. So static simulation. So simulation model that represent the system at a particular point in time only are called static. This type of simulation is often called Monte Carlo simulation. So maybe another day we're gonna talk about the Monte Carlo. This guy has really I like how he actually created the Monte Carlo simulation. If you know already the previous story, it's quite interesting. The dynamic simulation, normally most of the time we are doing dynamic simulation. And dynamic simulation, where actually the over time the system function change or system behavior change are simulating. So this is the difference between the static and dynamic, and I will also show there are some subcategories of dynamics, a dynamic simulation. So the discrete one, the variable of interaction change only at a discrete set of points in time. So I will also show a diagram, so maybe then it's easier to understand. So this one is discrete dynamic simulation, and this is continuous dynamic simulation. So you see, like here, if we read through factory operation, so discrete simulation, we are doing the factory operation like stamping, turning, milling, traffic analysis, road traffic analysis. We are doing this. The number of people queuing in a donut shop. So this is the what do you call the result? How the people are queuing in a donut shop in a daytime or during the operation. The number of customer change only when a new customer arrives or when a customer has been served. So only small information we can have here. This is quite static. But you see the continuous one, the variable of interest change over time. A simulation model for a car journey was created when the interest is on the speed of the car throughout the journey. You see, like speed and time. If you make the graph, you can easily see the situation in different time domains. So, so discrete and continuous simulation is quite explicit. So, but normally in model-based systems engineering, there is a very small room of application of those things. But of course, when it is necessary, you can also do this. And process simulation is something related with the production system. So in manufacturing, weather forecasting and product modeling, we are doing the process simulation. And here, this one may be also familiar to you from the last lecture. So model has physical, mechanical, and computer model. Then static, dynamic, and you see the dynamic things are needed to be simulated. And of course, the numerical or analytical simulation also related to dynamic. And the thing is, like dynamic things actually need to be assessed to understand the future behavior. So our point of interest most of the time with the dynamic system, not with the static system. So then simulation classification. So simulation can be classified with the one. So do you guys have the idea 1D simulation? 1D simulation is what do you call this? Simulink. Simulink is almost yes, it is doing the only simulation. There are some other softwares. I forgot there is a software also from Siemens, but from Dassault system there is another software called Daimler that doing only simulation. So 1D simulation normally used, let's say, try to understand what do you call the
change or chemical substance change. So those are predefined rules they have, and mostly those simulations are based on the mathematical model, and you cannot really do so many things, but to have some kind of initial idea, those simulations are not taking too much time. It is not like the CLT simulation that running, I don't know, few months. If you are, having so many small mesh, they more or less doing some kind of logical representation of your system behavior, and it's quite quick and easy, similar to Simulate. If you guys already have some experience. And 2D simulation also pretty much in the direction of 1D, but it is more, I would say, acceptable in a way, because it gives you some kind of quick analysis, because this also does not do not need so much computational power. So you can quickly make some simulations. So maybe as an example, I can show you the 2D and 3D. Maybe if you do you know aerofoil, right? Have you heard this word? Aerofoil. It's like the smallest section of a wing. So if you consider, so aircraft wing, if you consider, so the aerofoil is something like this. So this is the smallest section. So I think, I don't know, maybe 1,000 aerofoil actually creates one wing. So that is the smallest part. And normally we try to understand the behavior like how the wind is coming into this airfoil and behave. What are the behavior, or the pressure differences creating in this structure in different stages that we try to understand. And these actually give us quickly some kind of information about the whole wing surface area. And based on those analysis, we then go for the 3D analysis. So sometimes before going to the 3D analysis, people are doing the 2D analysis to have overview, and they can easily change the geometry somehow. It is very easy. So if you see here, there is a graph. So you see 1D, 2D, and 3D. There is a graph like the simulation time and cost. If you do 1D, it's quite straightforward. 2D is little bit more, and 3D is really very expensive and time consuming. So, so when you go for simulation, try to focus like what is your specific need, and based on your need, you try to define what sort of simulation you try to execute. Okay, then 3D simulation is great for determining the optimum design characteristics, and you specifically understand the system behavior. So 3D simulation is actually the last level normally we do. Yeah, and there are some others graphical representation also, like how we are considering the 3D simulation in relation to 1D simulation. You see, like the last one, figure 2, 1D model simplified from 3D cylindrical model, and this is actually the
cylindrical model for I think a composite structure, carbon fiber reinforced materials. Okay. So this also another way to do simulation. So maybe you guys are familiar with machine learning tools. It's the area of Sabina, though. People are now doing like the quick simulation. Mostly they also do not consider the 1D simulation or 2D simulation. So they try to create some kind of logic. So recently, we are actually studying some kind of bionic structure. And there we have seen that the computer model are not really so efficient to understand the bionic structure. So the bionic structure is like how the action goes in nature. So let's say the trees, the branches, and so they have it. They try to follow some kind of certain rules. So those kind of areas, people are trying to use machine learning. They try to use some kind of algorithms to understand the structural behavior, and they quickly doing the things. And you see, if they wanted to do the 3D finite element analysis, it takes really long time. So just for presentation, this is how the things are working. So simulation is only not confined with the 3D geometry. 3D geometry basically we try to go there when we have enough understanding of our system. Then only we go to the 3D simulation part. And okay. So MBSE and simulation relationship. This is quite straightforward, and we also discussed in the last slide. So model first, then simulation. So we try to figure out like how we're gonna create a good model, and that good model leads to a good simulation. So modeling is, I would say, the building block for the simulation. And if you see the figure, then if you consider the design context, then we break it down to the to the system level, to system subsystem. But I took from a publication. I'm not really agreed upon how they are doing like product then system breakdown. It's not really making any sense. However, the conclusion is you see the APA model or CAP model and simulation results. So our ultimate goal when we are doing modeling is simulation, but not all models can be simulated. Maybe you already heard or already seen from the seasonal model that all models cannot be simulated. Some models are really created for understanding. Some models created for running simulations to drive some kind of decision. So we can go to the next one, simulation building blocks. So this is very important when we are running, when we want to run a simulation, we have to set a goal. Then we need to create the model. As I have told you, the right models. Then we have to find out the relevance. We have to define the boundary, and then we can run the simulation and get the result. And of course, if you have the result, it does not means that your simulation is right. So you have to evaluate your result. And evaluation is not the last part. Rather, you have to try to improve the simulation. So these are the things normally we are focusing when we are doing some kind of simulation. So simulation steps. This is I'm not really very convinced. This is I would say, kind of straightforward thing, like a general presentation, like for simulation, how we are doing simulation, but for different types of simulation, there are different types of steps. So it is not always the truth, but you will have some kind of understanding. So we need to set up the goal, then we need to do the model, then we need to do the input data. We need to collect the input data and for the analysis, like in the evaluation, we need some kind of data. Then model transfer, translation, and run simulation. This is I took actually from a quite old book. And that time, simulation was not so easy. Like the graphical interface was not so defined like now what we have. And normally they try to convert the simulation to a programming language, and they run the simulation, and more or less they are doing kind of manual processes. So this is from that book. And also there is a YouTube video. This guy also shows a very nice way how to do the finite element analysis through programming language. It was also interesting. Then we have to do the verification and validation. So here there are some other way how people are telling that simulation is supposed to, when we're gonna do the simulation, and it's supposed to follow those steps. So you can read it through, but I think I would like to only discuss this one. So normally when we are trying to understand a system or try to find some kind of solution, or try to drive some kind of decision, we are doing experiment with actual system, experiment with the model. And the model is actually physical model, mathematical model, and mathematical model actually analytical or simulation. So you see, maths has a relation, it's a long relation with simulation. Then this also quite interesting steps. So problem formulation, simulation model, experimental design, and evaluation and iterate. So up to 4 I have given here. The phase 5 is like documentation, and phase 6 is implementation. So those two is not really part of the simulation. It is I think the post part of simulation. So yeah, I think we can go to the next one. And here we're gonna see some videos. First, I'd like to run this one. So this simulation, as I have told you, the airflow simulation. So this one is done with another software. It's called XFLFI. It's quite free. I think it's developed by MIT. And you see that during different angle of attack. So these are the angle of attack. How the pressure coefficient is changing. So here alpha is what we call the angle of attack. And you see, and based on this, you can actually, this is the pressure, you see, these are the arrows are the pressure. So when it is going in this, then here you are having more pressure. And can you guess, I would like to pause here. Can you guess that, like, what kind of decision we can make from this? Do you have any guess? Anyone? You? Okay. So you see, yeah, please.
So the angle of stop in the arrow.
Yeah. So this is the wing. Actually, it's not about the aircraft. It's only the wing and aerofoil is the smallest part of the wing. So if you cut the aircraft wing to a small section like this, then it will come. This is the wing and this is the thinnest part. So this thinnest part we are trying to see how it behaves. And from there, you see, we find the pressure gradient. And from this, we can identify like where the pressure is high. And you see here, this is actually the CG, center of gravity. And based on this, when we're gonna design the structure of the wing, we can easily identify that here I will have most pressure. So my structure is supposed to be what do you call more stronger here. So you see, like easily you can identify. So yeah, I can. And you see, this graph actually shows how the center of pressure, CP means center of pressure, is changing over time. Yeah, and you see how your center of gravity is changing. So this also you need to consider during the structural design that you're supposed not to put so much structure, that it is so heavy. Yeah, and from there we can have this coefficient of lift. Let's say like how much lift is producing by your your wing, then coefficient of moment, then this one is coefficient of lift over coefficient of drag. So how the drag and lift. So lift is good for the aircraft, drag is not good. So it is killing the coefficient of lift. So you see, it actually takes 10 to 15 minutes maximum. But I'm coming to that point. So this simulation actually, it took us almost 1.5, and it's still running. So yeah, we were having problem with the meshing. So now just have a look. So this is like the output of the simulation. We can see how the wind is behaving differently in different part of the wing. So this is actually the real outcome, and here you see this part. This is actually turbulence air, and this turbulence air is actually drag, and it's happening due to the drag and turbulence. Like if you have seen the tornado, then you see some kind of vortex. So this kind of things are really very bad for the wing. So the simulation result is not good here because the wingtip vortex is bad for the aircraft, because your aircraft will stall from here. So stall means you do not have any control on your aircraft. So we assume that from there we can make some kind of decision and we can change our geometry. So whereas we try to have this turbulence here, then we'll have more time to make some kind of decision, and we can have more time to control our aircraft, that this kind of scenario is not going beyond control.
I think. Yeah.
Yeah.
And why do we have more time to
This is actually related to aerodynamics. So when you have what do you call uh, giving a good example, let's say if you raise your hand, if you see if somebody is hanging here, do you have more time, or you can carry someone here longer time, right? But if somebody is giving you more pressure here, you cannot really hold them. Yeah, exactly. It's like when the turbulence is changing, you are losing the lead, and your whole body is getting like what do you call it, stone. So it's not more floating. So that's why we always try to have as close as possible from the turbulence. Okay. Okay, then again. So probably this is your assignment, but I'm showing you the solution from the assignment. So here we'll see some finite element analysis. So I think you will understand like where we wanted to put the load and see how the structure is based on this load. Okay, so for this one, for setting, so you need to first fix the structure. So let's say the computer does not understand that, where you will put the load and which one is static and which part will be dynamic or move through the load. So you have to tell the computer that this part and this part will be fixed, and the other part you're supposed to put the load to the other part. So these are the settings actually. I think I made it like this because maybe I do not need to describe something when you have the problem. So immediately you can see and simulate. So this will help. So you see this particular part is where we're gonna give the pressure, and this is actually called the mesh. And mesh is actually it mesh has different structure. It could be triangle, it could be pyramid type. And you see this is the outcome of the simulation. And you see how when you are you know giving the load and how the structure actually behaving. So this is how, and here is actually the stress, displacement, and strain. So I think you guys already know this stress strain curve. So this kind of curve, so this I think pretty common. Okay, so sorry, I have to go another one. So here is another simulation. So this one is not actually simulation. This one is a kind of presentation or animation how the reactor planet. I don't like talk. So
because why this is also from YouTube. Why I try to do this, because without having this, it would be a little bit difficult for you guys to understand the other simulation. The other simulation is done in enterprise architect by Sabine. So this is actually the landing gear lever, and with specific settings, the landing gear actually behaves differently. So extraction, retraction, and another one is what do you call? When it is in the ground, then you need to drive, so steering. So these three mode it has, and it is quite monotonous video. So now the gear is extended. So you see inside the aircraft how it works. Okay, but this is actually the gives me the steering, how the nose gear is steering. So these two are not you know, steering. So only the nose gear is steering. Okay. But we have done this one for small aircraft, so there is no hydraulic system. And only the sequence, we try to simulate the sequence. Is the time is already over? Sorry.
No.
Ah, so you see
Yeah.
the setup, transmission.
Simulation. There are some kinds of parts where the automatic simulation can run through, and then you have some triggers. Of course, you can also optimize them. Currently, in this simulation, we do not optimize because we say it depends on which state of the aircraft you want to simulate. So you have the manual trigger where you say, okay, now this is run through. You can also check with this in some log files for this process, and then check if it is behaving like you want. And out of these log files, you can possible also generate, for example, people tagging that can analyze reactions.
Yeah.
Okay.
So I think yeah.
Yeah.
So and this is actually the last one, but I will not take this post-simulation. Post-simulation is very important for model systems engineering, because you see, we found so many 1D, 2D, 3D, and the static, dynamic, so many types of simulation, right? So when you are designing a complex system, you need to bring them together and see how one is behaving in relation to other. And this is the complex task really, and most of the time we are failing there. The technology is not really so mature that we can do whatever we like. But of course, people are working, so we have to be optimistic. And there's a nice video there. If you guys have time, just have a look. So that's all for today. I actually wanted to show you how to do simulation in SolidWorks, but maybe next lecture if you have some time. Yeah, I can. Mostly the other videos have the sequences, But of course, I can make a little video maybe if you want.
Ja.
I